So as we start into section 3.7 on optimization, I want us to work this first example kind of slowly, and as we do, we'll develop the method that we'll use for future examples. This problem does come from our textbook. It's problem number 9 from page 224. And the problem says find two positive numbers such that the sum of the first and twice the second is 108, and the product of the two is a maximum. So let's maybe start off by figuring out what it is that we're asked to do. What's our objective? Our goal is to find two numbers whose product is the maximum. So our objective is to maximize the product of the two numbers. Well, they can't just be any two numbers. I can't take a million times a billion. It has to be two numbers such that the sum of the first and twice the second is 108. So there's a constraint on what the two numbers can be. So if we let I can just write it in words. The first one plus 2 times the second equals 108. So in all of these problems, which we'll call max and min problems, our objective is going to be either to maximize or minimize some quantity, and we're going to have some constraint, which puts some restriction on whatever the variables are. So let's go ahead and name the variables. So let's let the numbers be x and y, thinking of x as the first of the two numbers and y as the second. Let's translate our objective and our constraint into variables. So what we want to do is maximize the product, which I'll call P, subject to the constraint that the first number, x, plus twice the second number equals 108. So we're going to call this first function our objective function. That's going to be the function that you're trying to make as large or as small as possible. And the second equation here, we're going to call the constraint. Now that we've written that down, I can kind of give you what the method's going to be for solving. So first of all, we're going to do what we just did. We're going to define variables. And write equations for the objective function and the constraint. For our second step, we're going to solve for a variable in the constraint and substitute into the objective function. At that point, the objective function will be a function of one variable alone, and then we can use derivatives to find maximum and minimum. So we can find the critical numbers of the objective function by taking the derivative. And finding where it's either 0 or undefined. And then last of all, we're going to interpret our answers. Now that's a general outline. We're going to have to be flexible in applying it sometimes. For example, sometimes when you write things down, everything's already captured in the objective function. There's not a separate constraint. In other examples, you might have several constraints, and you'll solve for a variable in each one, but with the goal of making the objective function a function of one variable alone. Sometimes also there are domain issues, so that when we're looking for an absolute maximum, we might have endpoints that we need to consider, as when we found the absolute extrema of a function on a continuous function on a closed interval. So all of these can play in, but this is kind of a good general outline of how we'll solve a problem. So let's start applying these steps to this particular problem. Notice that the first step is already done. We've defined our variables. We've written down our objective function, our constraint. Now let's solve for a variable in the constraint and substitute back into the objective function. Looking at this equation, we could solve for either y or x, but notice it's going to be easier to solve for x. So let's do that. So remember, we're solving for a variable in the constraint. So in the constraint, x plus 2y equals 108. We can subtract 2y from both sides. To get x is 108 minus 2y. And then we're going to substitute into the objective function. So we'll have p equals 108 minus 2y multiplied by y. So 108y minus 2y squared. Notice now that my objective function only has one variable y in it. So if I want to, I can kind of emphasize that by using function notation over here. P of y is 108y minus 2y squared. And that's step 2. Now for step 3, we're going to take the derivative. P prime of y is 108 minus 4y. This is never undefined. So let's set it equal to 0 to find its critical numbers. That's going to be when 108 equals 4y. So y is 108 divided by 4, which is 27. So it appears that when y equals 27, we're going to have our maximum. If we wanted to check to be sure that it's a maximum, we could maybe use a second derivative test. Notice that p double prime of y is negative 4, which means that the graph is concave down at this critical number. So if it's concave down at a critical number, that means that a critical number is the location of a maximum. Now we're supposed to find both numbers. If I want to find out what x is, I can substitute back into the constraint. So x is going to be 108 minus twice 27, which is 108 minus 54, or 54. And then finally, to state what our answer is, we can say the maximum product is attained when the numbers are 54 and 27, and the product will be x times y. So p will equal 54 times 27, which is 1458. And that takes care of the last step.